Hello students, welcome to this video module on electromagnetic waves, reflection and transmission at oblique incidence. In the previous video module, we discussed about reflection and transmission of electromagnetic wave at a boundary between two linear homogeneous media, but that was a case of normal incidence in which the light ray incident normally to the boundary, or that is making an angle 0 degree with the normal, that is known as normal incidence. So we discussed about reflection and transmission at a normal incidence in the previous video module. So next we are going to discuss about reflection and transmission at oblique incidence, that is at any other angle other than 0 degree on a boundary between two linear homogeneous media. So here you can see an incident wave, a wave incident on a boundary between two linear media. You can see two media there, two medium there, one is medium 1 and medium 2. So the electromagnetic wave incident at an angle theta I, you can see here theta I, a part of that reflected at an angle theta R, and another part transmitted to the next medium with an angle theta T. And Ki, Kr and Kt represents the wave vectors in medium 1 and medium 2 respectively. But we know that Ki and Kr are same because they represent the wave vectors in the same medium. Reflection and transmission takes place in same medium. Now let us see the wave equation for incident wave, reflected wave and the transmitted wave. Let the electric field part of incident wave is represented by Ei complex R comma T. In the previous case, we denoted that by Z comma T, specified the direction as Z. Here we are representing the direction as any general direction R, the direction vector. So that is equal to E0 I complex, the complex amplitude of electric field, times exponential I Ki dot R minus omega T. In the previous case, it was e raised to the power I Ki dot Z minus omega T. Here it is e to the power I Ki dot R minus omega T. And the corresponding magnetic field intensity of incident wave is represented by Bi equal to, it is actually Bi is equal to 1 by V1 times magnitude of Ei times a vector which is perpendicular to the propagation as well as electric. So how to get a direction perpendicular to the propagation direction as well as electric field? That is Ki cross Ei. So Ki cross Ei gives a vector which is perpendicular to K, that is the propagation direction, and E, that is electric field. So we know that magnetic field is perpendicular to the electric field as well as to the propagation direction. That is why this notation, the Ki, this is Ki, unit vector Ki, its magnitude is 1. That is used here, Ki, unit vector Ki, Ki cap. Similarly, the intensity of reflected wave electric field is given by ER equal to E0 R complex exponential IKR dot R minus omega T, and BR is equal to 1 by V1 times KR cap cross ER complex. And the transmitted wave, that is in the second medium, so ET complex equal to E0 T complex exponential I Kt dot R exponential I Kt dot R minus omega T. Now we know that when the electromagnetic wave propagates from one medium to another, its frequency remains constant. So omega 1 or omega I, omega R, they are equal actually. They are equal to omega T equal to omega. So we can write omega is K times V. So K1 V1 or Ki V1, Kr V1, because velocity of incident and reflected are same in the same medium, Kt times V2. But Ki and Kr are same. So we are taking the V1 from there. So Ki equal to Kr equal to V2 divided by V1 times KT. But we can replace V2. We know that V equal to C by N. So using that, N, so you can plug in for that. Instead of V2, it is C by N2. And instead of V1, it is C by N1. That gives N1 by N2 times KT. Now we know that at the boundary, the fields must be continuous by applying the boundary conditions. So that shows that EI complex plus ER complex must be equal to ET complex. And also BI, the magnetic field components also must be continuous. So that is BR complex equal to BT complex. So in a general form, we can write this as the amplitude times e to the power I ki dot r minus omega t plus again amplitude times e to the power I k r dot r, small letter r, minus omega t must be equal to amplitude times e to the power I k t dot r minus omega t. So this shows the electric field components and the magnetic field components are continuous at the boundary. That means at z equal to 0. At z is equal to this bracket you can fill either with electric field E or magnetic field B. So that is why it is a general form is written there. Okay. The boundary conditions must hold at all places on this plane. This is the boundary and this is the propagation direction. So, and you can see this is z equal to 0. So here you can see any point. This is all x or y. These are x and y's. So anywhere this boundary condition must be satisfied, not only at this point. So anywhere here or whatever. So the boundary conditions must hold at all points on the plane and for all times also. So these exponential factors that we discussed earlier must be equal. Otherwise, if there's a small change in x, that will destroy the equality. So we know that the time factors are already equal. We can write the spatial factors. So there are two factors, k dot r minus omega t. So the spatial factors also must be equal in this equation for the reason that we said above. So everywhere the spatial fact, everywhere on this plane, the equations must be continuous. Not only at this point where we marked at the center. It's not like that. So the wave can propagate like this, or the wave can propagate like this. In this direction, anywhere it can propagate. So anywhere on any time, that must be continuous. So the time fact. So there are two factors. One is k dot r factor, and another is the time component. So the time component already equal. So we then the spatial components also must be same. So for that, what is the required condition is ki dot r vectors equal to kr dot r equal to kt dot r, or in magnitude terms we can write this as x times the x component of ki plus y times the y component of ki, because this is a dot product. So maximum value is for the angle k dot r. We have to find the product of similar terms only. So r actually consists of x I cap plus y j cap plus z k cap. No need to consider this because there is no component of z component is not there in the propagation vector. So that is why x and y components we are taking. So x times ki. So k also has got the x component and y component. So that is why ki x component into x. Okay, plus ki y component into y. That is why this term. In the same way for the reflection also, x into x component of reflection, x into the x component of kr. Kr is the wave vector for reflected component, and y times y component of kr. That must be equal to the x times the x component of kt and plus y times y component of kt. Okay, now this is true for all x and y's. And you know this equation, this equation only hold if the components are separately equal. So these must be separately equal. So if we keep x equal to 0, then the y components must be equal. That is why ki of y equal to kr of y is equal to kt of y. In the similar way, if you put y equal to 0, then the x components must be same. So that means for this equation to be true, the x components must be separately equal and the y components must be separately equal. That is why this statement. Or this leads to a general conclusion that the incident, reflected, and transmitted wave vectors form a plane. It's called the plane of incidence, which also includes the normal to the surface. So, or we can say this is the first law of reflection, the first law of optics in general, I think. The incident ray, reflected ray, transmitted ray, and the wave vectors of these forms a plane, which includes the normal to the surface. Okay, so so through this we proved we reached the first law of optics. Now, again, continuing from this, the first part of this equation, we are taking ki of y by putting x equal to 0. By putting x equal to 0, we reach ki of y equal to kr of y equal to kt of y. And also when y equal to 0, we reach this one. Okay, so by taking this, it implies that ki sine theta I equal to kr sine theta r equal to kt sine theta t. Because when you consider this diagram that we drawn initially, you can see that this is the incident wave vector ki. You can divide this into two components. The ki, and this is theta I. We can divide this into two components, right? This is called the ki. What is that? Ki cos theta I component, and this is the ki sine theta I component. So this is the y component of ki. This is the y component of ky. Ki of y, that is ki sine theta I, that is y. So instead of writing like this, they wrote the complete magnitude. So this is only the representation ki of y, the y component of ki. Actually, what is y component of ki? That is ki sine theta I. Similarly, what is the y component of kr? This is r, kr. This is kr. You can divide this also into two components. This is kr sine theta I. That is the y component. So you see here ki sine theta I equal to kr sine theta r. This is kr sine theta. This is equal to kt sine theta t. Oh, this is actually kt. You can divide this into, this is kt cos, and I mean kt, and this is kt sine theta I. Okay, so ki sine theta I equal to kr sine theta r equal to kt sine theta t. Now, so this shows that the angle of incidence theta I, here theta I is the angle of incidence and theta r is the angle of reflection. We know that ki and kr are same. That shows that sine theta I equal to sine theta r, or that shows theta I equal to theta r. This is actually the second law of optics, or that is also known as the law of reflection. The angle of incidence is equal to angle of reflection. This is the known as the law of reflection, or the second law. So we reach the second law also. Now we consider the same equation again. Ki sin theta I equal to Kr sin theta R equal to Kt sin theta t. In the previous case, we connected the first two. Now we consider this first one and last one. So you can write Ki sin theta I equal to Kt sin theta t. So that is sin theta t divided by sin theta I equal to Ki divided by Kt. So what is Ki? Ki is equal to omega divided by V1. This is omega divided by V2. So you will get sin theta t divided by sin theta I equal to omega cancels V2 divided by V1. That is also equal to N1 divided by N2. Or you can write this as N, or the ratio of ratio of the refractive index of the medium. So this is the Snell's law. Sin theta, so you can write sin theta I, sin I by sin R. This is the general way that we learned. So sin theta I divided by sin theta t equal to N2 by N1, that is equal to N21 refractive index of the second medium with respect to first medium. So here we reach the law of refraction, or also known as the Snell's law. Now again, we have to find the x. So what we derived now, the three laws of optics: first law, second law, and third law. The next part of the discussion is about the relation between intensity of reflected part and transmitted part of the incident wave. We have to get the intensities in terms of incident wave. So for that, again, we are considering the boundary conditions. Okay, so these are the boundary conditions that we learned. Okay, so the boundary conditions applied to the above equation, this equation that we derived. So the boundary condition, the first boundary condition, you can see here E1 times, sorry, epsilon 1 times E0 I plus E0 R, the perpendicular components actually, equal to epsilon 2 E0 T. The next one is for magnetic field components. They must be continuous. And evidently the third equation, the fourth equation, 1 by mu times V0 I complex plus V0 R complex xy equal to 1 by mu 2 times V0 T complex. These are the application of boundary condition to the above equation. Okay, and where we used B0, instead of B0 we can use 1 by V times K cap cross E0. Okay, yeah, these are the component representations also. Evidently the component representations are shown here. Okay, now what is you can see these are the z component. So E epsilon 1 minus E0 I sin theta I plus E0 R sin theta R. How we got this minus E0 I sin theta sin theta I and E0 R sin theta R? Here you can see this is K1, the incident electric field component. Incident electric field component can be divided into two. One is the sin theta component and the cosine theta component. So the sin theta component is see in this diagram, this is EI. You can see the direction of EI, and if you draw a normal here, this is the angle theta I. If this angle is theta I, here this angle also theta I, then the electric EI can be divided into two components. One is EI sin theta I. You see that is against the z axis. That is why negative term came there. And when you discuss about the reflected part of that, see this is the reflected one, in that this is the E0R sine theta, that is along the z direction. That is why it is taken as positive. And look at the case of transmitted wave, that also we can divide into two components. One is this like this, so that is why it is minus E0 T sine theta T. So you see here minus E0 T sine theta T. Okay, so this is actually from the first equation, the boundary condition that we discussed. The z components are there. Okay, And for the second one, that's nothing in this. Okay, and the third equation we can write is the xy component, along the xy, E0I plus E0R. So what you can write is, or the third or fourth, I mean. So what is the third equation you can write? See, the same diagram, if it this is it the sine theta component, this is the cos theta component, so you can write this as E0I cos theta component, and here if this is sine theta component, you can write this is the E0I cos theta component. Okay, so both are in the same direction, upward direction. That is why both are positive. In the same way, here also this is E0t cos theta t component. That's also in the upward direction. So everything positive. So that is why the third equation, third boundary condition leads to E0 I cos theta I plus E0 R cos theta R equal to E0 T cos theta T. Now, the fourth boundary condition, you can apply the fourth boundary condition, and magnetic field you can replace by 1 by V times electric field. So that also employed here. So 1 by mu1 V1 E0 I minus E0 R, the reflected part in the opposite direction, and that's equal to 1 by mu2 v2 E0t. This is actually a general case of what we discussed in the case of normal incidence. So this is a general case. Okay, so so we used the four boundary conditions and reached the equations. The first equation we got from the first boundary condition. This is in the third boundary condition, and this is from the fourth boundary condition. Now we have to solve. We have to solve these equations. So using the laws of reflection, what is the law of reflection? Law of reflection says that theta I equal to theta R. That you can apply here. So theta I and theta R same means then sine theta I and sine theta R will be same. So this equation you can write E1 sine theta I is a common factor minus E0I plus E0R complexes equal to what? E2 times sine theta t with a negative sign here and an E0 t complex term, right? Then there will be another term, that is you can again rearrange this into you can take the sine theta I to the other side. So this will become sine theta I from here to this, it will be divided by sine theta I. So what you can write now is E0 E0I minus E0 R equal to the minus sign gets cancelled from the other side, equal to E0 T. Then there is an epsilon 2. What is sine theta T by sine theta I? Sine that is, we already learned the law of third law, or the law of refraction, or Snell's law. What is that? Sine theta I divided by sine theta T equal to n2 by n1. Here it is sine theta t by sine theta I. So it will be reversed, n1 by n2. So you can add one n1 by n2 also here. So what you got, and also one more term, that is divided by epsilon 1, of course. So E0I minus E0R equal to epsilon 2 by epsilon 1, n1 by n2. Okay, now what is epsilon 1 and epsilon 2? You can rearrange this. See, V1 equal to 1 by root of mu1 epsilon 1. Therefore, when you take the square of this, it will be V1 square equal to 1 by mu1 epsilon 1. So epsilon 1 equal to 1 by V1 square into mu1. And epsilon 2 equal to, and epsilon 2 equal to 1 by v2 square mu 2. So what you can write, instead of epsilon 2 divided by epsilon 1, it will be V1 square mu1 divided by V2 square mu2. Okay, and already there is one n1 by n2. And another thing is that, okay, let it be there. So there is there is an n1, n2 in the equation. So you see here, I'm going to rearrange again. E0I complex minus E0R equal to, instead of this, we can write V1 square divided by V2 square, mu1 by mu2, then one there is N1 by N2 times E0T. But this, what is this N1 by N2? N1 by N2 is V2 by V1. So one of the V2 and V1 cancel. So V1, so this will become mu1 V1 by mu2 V2. Okay, so that term, or this is also equal to mu1 by mu2 times n2 by n1. In that way also you can write. So that term is replaced by this beta. Okay, so we got it. The first equation, we substituted theta I equal to theta r in this first equation. Then we took the sine theta I to the opposite side, then applied Snell's law, and then some simplifications for this velocity and epsilon 1 and epsilon 2 components, and simplified, and finally we got this beta. I hope you remember we discussed about this beta in normal incidence case also. Okay, so the same thing here. So beta is actually mu1 v1 by mu2 v2, or mu1 n2 by mu2 n1. So that is this beta term. So we reached at this equation. This is an important first equation. Similarly, so this one we got. Okay, and the same way we can write the next equation, that is the cos theta equation. So in the same way you can write the cos theta equation. Theta I and theta r are same. So similarly, the second equation, the cos theta equation, also we can substitute theta I equal to theta r. So cos theta I, cos theta, you can take it as a common factor. You will get E0 I complex plus E0 r complex equal to cos theta t divided by cos theta I times E0t. And this can replace to alpha times E0t. What is alpha? Alpha is cos theta t divided by cos theta I. So we got the next equation, E0I plus E0R equal to alpha E0t. Earlier we got an equation E0I minus E0R equal to beta E0t. So we got two equations in E0I, E0R and E0t. So we have to solve these two equations to get the value of E0R and E0t in terms of E0I. That is the only known thing is E0I and alpha and beta. We know this theta I and theta t things we know. Also beta we know. So alpha and beta we can calculate using these known factors, alpha and beta. Okay, so now solve these two equations. How to solve these two equations? You can either you sum these two equations. When you sum these two equations, E0R and E0R get cancelled. So 2 E0I equal to E0t alpha plus beta. So that is why E0t equal to 2 divided by alpha plus beta times E0I. Substitute this in the first equation, you will get E0R equal to alpha minus beta by alpha plus beta times E0I. So we got an expression for the complex amplitudes of reflected part and incident part of electric field in terms of the incident intensity of electric field, and the alpha and beta, which in turn alpha depends on the angle of incidence and angle of refraction. Actually, the theta t is actually angle of transmission, or we can say it is angle of refraction also. And beta depends on the relative permeabilities and the speeds or refractive indexes of the. These equations that we derived now, they are actually known as Fresnel's equations. Fresnel's equations for polarization in the plane of incidence. There are two other Fresnel's equations giving the reflected and transmitted amplitudes when the polarization is perpendicular to the plane of incidence. Now, we know that alpha is equal to cos theta t divided by cos theta I. Now rearrange cos theta to root of 1 minus sine square theta, and using the Snell's law, sine theta t equal to n1 by n2 times sine theta I, we'll get this expression for alpha. Okay, now there are two special cases. One, when the angle of, for normal incidence, the first special case is normal incidence. Normal incidence angle of incidence theta I is equal to 0. That means normal incidence means the angle, the light ray or the wave incident through the normal, along the normal. So all angle we measure with respect to normal. So if a wave incident through normal means the angle of incidence is 0. So this expression will be, you can write E0R equal to 1 minus R, because in case of theta I equal to 0, theta t also equal to 0. So 0, I mean, yeah, then cos 0 is equal to 1 by 1. In that case, alpha will be equal to 1. So when alpha equal to 1, you can write E0 R equal to 1 minus beta divided by 1 plus beta times E0 I, and also E0 T complex equal to 2 divided by 1 plus beta times E0 I. This is exactly what we derived in the case of normal incidence. So normal incidence is actually a special case of this oblique incidence, because normal incidence angle is theta is 0. So we can derive the normal incidence case that we learned in the previous video module through this way also. So after completely deriving this, you can put the value of theta equal to 0. Otherwise, you can directly derive as we did in the previous video module. Now, there is another case. This is about normal incidence we discussed. Now, we can discuss about grazing angle. When the light ray incident along the surface, like this, see, if this is the surface, this is the normal. If a light ray incident like this, then the angle of incidence will be 90 degree. Okay, so this is a grazing incidence. Grazing incidence, just opposite to that of normal incidence. At grazing incidence, theta I is equal to 90 degree. When theta I is equal to 90 degree, the alpha theta, what is cos 90? Cos 90 is 0. So division with 0, it gives an infinite answer. Or we can say the light ray diverges, alpha diverges. Alpha diverges means there is no refracted part, there is no transmitted part. Total, the wave will be totally reflected. So if the light, there will not be the light, it will be like this. The light ray will be completely reflect only, no transmission in that case. Okay. So we discussed the two special cases. One is the normal incidence and other is the grazing incidence. Now, there is an intermediate angle between these two, between 0 degree and 90 degree. There is another angle called Brewster angle, theta B. Is called the Brewster's angle. Okay, the Brewster's angle is the angle at which the reflected wave is completely extinguished. So when the light ray incident at Brewster angle, the refracted ray and the reflected ray will be perpendicular, and one will be polarized also. So let us see what is this Brewster angle. So you can write sine square theta B equal to, so the equation that we already derived. There is an intermediate angle between angle theta equal to 0 and theta equal to 90 called the Brewster angle, at which the reflected wave is completely polarized. So according to this equation, the boxed equation that we derived right now, this is possible. That is, the reflected wave is completely polarized, possible only when alpha equal to beta. So we already derived the expression for alpha. Alpha is cos theta t by cos theta I, and we deduce this expression, and we can equate this to beta as per the condition written above. So then square on both sides, you will get 1 minus 1 n1 by n2 sine theta I square by cos square theta I equal to beta square. So you can write 1 minus n1 by n2, or n1 by n2 square sine theta I sine square theta I equal to beta square times cos square theta I, or you can write cos square theta I here itself, cos square theta I. Now rearranging this, what we can write is this is equal to 1 1 minus n1 square by n2 square sine square theta I equal to beta square cos square theta I. But I'm going to write beta square, instead of cos square theta I can write 1 minus sine square theta I. Now again, some more rearrangement on this. We can write this beta square can be taken in, so this become beta square here and beta square here also. Now again rearranging, 1 minus beta square equal to n1 square by n2 square sine square theta I minus beta square sine square theta I. But what is n1 by n2? Or you can again rearranging, this can be written as 1 minus beta square equal to, you can take sine square theta outside. So n1 square by n2 square minus beta square times sine square theta I. Okay. So from this we can write sine square theta theta I is from here onwards, it is theta B, called the Brewster angle. Sine square theta B equal to 1 minus beta square divided by n1 by n2 whole square minus beta square. Okay. This is the expression we got for sine square theta. Now we already know that for a typical case of what is called for the relative permeability of the medium is close to the relative permeability of vacuum. So using that, what will be the value of beta? Beta, we already know beta is equal to mu1 n2 divided by mu2 n1. This become approximately equal to n2 divided by n1. So using this, we can write sine square theta b. So sine square theta b is equal to 1 minus beta square divided by. Now instead of this n1 by n2, you can write 1 by beta whole square minus beta square. This can be 1 minus beta square divided by, this can be written 1 minus beta square. So this become beta raised to 4, and divided by beta square is there, that will come to the top. So beta square. Now this can be written as 1 minus beta square times beta square divided by this 1 square, 1 minus beta to the power 4. You can write this as 1 to the power 4 minus beta to the power 4. That you can write as 1 square whole square minus beta square whole square. So this is actually 1 minus beta square into 1 plus beta square, right? So we can write it as 1 minus beta square into 1 plus beta square. 1 minus beta square cancels. So sine square theta is equal to beta square divided by 1 plus beta square. Now, continuing, what is sine square, or what is sine square theta b? We derived as beta square divided by 1 plus beta square. Now, from here, okay, you can do one thing. You can divide this with cos square theta b. So sine square theta b divided by cos square theta b, that is 1 minus sine square theta b. So 1 minus beta square divided by 1 plus beta square. Okay, that is equal to, here you can take the LCM. So this become beta square divided by the 1 plus beta square will get cancelled. So 1 plus beta square minus beta square, it will become 1. So sine square theta by cos square theta is equal to beta square beta square divided by 1. So it is beta square. So that is equal to tan square theta b is equal to beta square. So what is tan? So tan theta b equal to beta. So that shows tan theta b equal to, what is beta? Beta is equal to n2 divided by n1. That is n21. This is actually known as the Brewster law. Tangent of the angle of the Brewster angle is equal to refractive index of the medium. So hence we derived the Brewster law also. Um, the diagram here shows this particular graph shows um, uh, the transmitted versus the transmitted and reflected amplitudes as a function of angle of incidence. You can see the transmitted intensity and the reflected intensity. Actually, the ratios of transmitted to incident and the reflected to incident as a function of the angle of incidence here. Okay. This graph, the negative number indicates that the wave is 180-degree out of phase with the incident beam. Now we are continuing our discussion to the derivation of reflectance and transmittance. So for that, we are taking the expression for intensity. We learned the expression for intensity as I is equal to half epsilon V1 E0 I square. This is the case of normal incidence where angle is 0. But for general case, there will be a term cos theta I also will come. For the case of normal incidence, we substitute this angle as 0, and that is why the incident intensity is up to this only. But here in the general case, it is times cos theta I also will come. And for reflected intensity, the half times epsilon 1 V1 E0 R square cos theta R, and transmitted intensity half times epsilon 2 V2 E0 T square times cos theta T. Now reflectance, it is a ratio of it's a ratio of reflected intensity to incident intensity. So when we substitute this, you can see that half, okay, it is like R equal to E0, 1 by 2 times epsilon 1 V1 E0 I square cos theta I divided by 1 by 2 times epsilon 1 V1 E0 R square cos theta R. But theta R and theta I are same. Therefore, these are same. Half cancels. Epsilon 1 happens in the same medium. So V1 cancels. So only term remaining is E0 R square. I'm sorry, here it is R. Here it is I. Okay. Here it is. Okay, so E0R by E0I whole square. And we already derived E0R. What is E0R? It is alpha minus beta by alpha plus beta times E0I whole square divided by E0I whole square. So E0I also cancelled. That is what this term. So reflectance is given by alpha minus beta by alpha plus beta whole square. In the same way, we can derive the transmittance is equal to alpha beta times 2 by alpha plus beta whole square, just by substituting intensity of transmitted beam and intensity of reflected beam. So you can see the cos theta t and cos theta I there, and this cos theta t and cos theta I can be replaced by the same calculation that we followed in the previous slides. Okay, so we get alpha beta times 2 times 2 by alpha plus beta. Because we already in the previous slide this cos theta t by cos theta I is actually alpha. That is why this alpha came there. And epsilon 2 by epsilon 1 and v2 by v1, and we derived that is equal to beta. If you have some doubt, you can refer the calculation of beta in the previous video module for normal incidence. Okay, so this is the expression for R and T, and also we know that R plus T is equal to 1. And here you can see the plot of as a function of the angle of incidence. R and T are plotted as a function of angle of incidence, and you can see that the sum of these two quantities are equal to 1. Okay, students. So here in this video module, we discussed about oblique incidence. This is a general case of electromagnetic wave on a boundary between two linear homogeneous medium incident at any angle. So and through that we derived the laws of optics, the first law, second law, third law. Third law is also known as the Snell's law. And we also proved the Brewster law. Then we proved the reflectance and transmittance. And all these parameters are discussed, and this plot of reflectance and transmittance with respect to angle of incidence also derived. I hope this video module help you to study this. Okay, students, thank you. Bye.